Imagine for a moment an object adrift in the cosmic dark. It possesses the gravitational might of a million suns, a behemoth of staggering density. Yet it is utterly, profoundly invisible. It casts no shadow because it emits no light, no glow in the visible spectrum, no telltale hiss of radio waves. It doesn't burn, it doesn't radiate, it doesn't announce its presence in any way our telescopes are designed to see. It simply is, a ghost in the machine of the universe, defined by a single, fundamental force: gravity. And yet, against all odds, astronomers just found one. A phantom object lurking 10 billion light-years from Earth. They didn't see it. They saw what it did. They saw where it reached out across the void and pinched a stray beam of light. Here's the truly wild part. This dark object is roughly 100 times smaller in mass than the tiniest cosmic structures we've ever managed to spot using this technique, known as gravitational lensing. Finding it is like hearing a single pin drop in a hurricane from a continent away. It's a new record in cosmic detection. To understand how they did it, we need to visit the scene of the crime. This is an Einstein ring, cataloged as B1938 plus 666. It's one of the most beautiful and profound predictions of Albert Einstein's theory of general relativity made real. Einstein taught us that massive objects don't just sit space. They fundamentally warp the fabric of space-time around them. Imagine a bowling ball on a stretched rubber sheet. The sheet curves around the ball. Now, if you roll a marble past the bowling ball, it won't travel in a straight line. It will follow the curve in the sheet. Light does the exact same thing. When light from a very distant galaxy travels toward us, its path can be bent if it passes by a massive object, like another galaxy, along the way. This foreground galaxy acts like a cosmic magnifying glass, a gravitational lens. And if the alignment is just right, the distant galaxy, the foreground lensing galaxy, and us, here on Earth, all in a perfectly straight line, that bent light appears to us not as a point or a smear, but as a near-perfect circle of light, a halo of a galaxy far, far away. That is an Einstein ring. General relativity playing the role of a cosmic sculptor. Now, look closely at B1938 plus 66. For years, we saw it as a beautiful, complete ring. But when astronomers pointed an unprecedentedly sharp array of telescopes at it, they saw something new. In these ultra-sharp radio images, one arc of that ring narrows and distorts. It's as if an invisible finger reached out across 10 billion years and pressed into the beam of light, leaving a subtle indentation. That subtle wobble is the tell. It's the fingerprint left at the scene. The main lensing galaxy creates the beautiful, large-scale ring. But this tiny secondary distortion, that's caused by something else, something much smaller and much closer to the light's path. So, what pressed the light? The calculations point to an invisible mass equivalent to about 1 million suns, a ghost with undeniable weight. Catching this cosmic ghost required a telescope not built of steel and concrete, but of geography. It took a super telescope the size of planet Earth. This wasn't the work of a single observatory. It was a global collaboration, linking some of the most sensitive radio dishes on the planet. The Green Bank Telescope in West Virginia. The 10 dishes of the Very Long Baseline Array, stretching from Hawaii to the Virgin Islands. And the European VLBI network, a consortium of telescopes across Europe, Asia, and South Africa. They used a technique called Very Long Baseline Interferometry, or VLBI. The principle is ingenious. By recording the signal from a cosmic object at each of these widespread telescopes and noting the infinitesimally small differences in the signal's arrival time, you can combine the data. You effectively create a virtual telescope with a diameter equal to the largest distance between the dishes, in this case, thousands of kilometers. Stitch the signals together with a supercomputer, and you get a microscope for the universe, capable of seeing details 1,000 times finer than the Hubble Space Telescope. But even with this incredible image, the discovery wasn't guaranteed. Then came the heavy lifting, custom, painstaking numerical modeling. Scientists built a perfect digital twin of the lensing system. They told their computers, this is the mass of the main galaxy. This is the position of the background light source. Now show me exactly how every single pixel of that ring should look. They created a flawless, idealized version of the ring. And when they subtracted this perfect model from the real, observed data, something was left over. A residual, an error message from the cosmos. The model was perfect, unless something extra was lurking there, unaccounted for. It was. The tiny pinch in the arc popped out immediately. The data screamed that there was a small, compact mass right there, warping the light just enough to be noticed. So what is this million solar mass ghost? The two leading possibilities are equally fascinating. It might be a compact, isolated clump of dark matter, a pure concentration of the mysterious substance that holds galaxies together. Or it could be a tiny, dormant dwarf galaxy, one so ancient and inefficient at making stars that it's now almost entirely composed of dark matter and cold gas, with barely any stars left to shine. Either way, it's a ghost with weight. Why does finding this one object matter so much? Because it takes us directly into one of the biggest mysteries in all of science, the nature of dark matter. We know from the way galaxies spin and the way light bends around them that about 27% of the universe is made of this stuff. It is the invisible scaffolding upon which our visible universe is built. Yet it doesn't interact with light or any other form of electromagnetic radiation. We only know it's there because we can feel its gravity. Our leading theory, the cold dark matter model, doesn't just predict vast, smooth halos of this stuff around galaxies. It makes a more specific, testable prediction that these halos should be messy. They should be filled with countless smaller, denser clumps, or subhalos, ranging from the mass of stars to small galaxies. Our own Milky Way should be swarming with thousands of them. The problem is, because they're dark, they are almost impossible to find. This is where the pinch in B1938 plus 666 becomes so important. Finding this one, so incredibly far away and with such a relatively low mass, is a huge boost for that theory. It's direct evidence that such small clumps do exist, just as predicted. Furthermore, by measuring the clumpiness of dark matter, we can start to constrain its properties. Is it made of heavy, slow-moving particles? Or something more exotic? The number and size of these clumps can help us tell the difference. This discovery, detailed in 2 studies published on October 9, 2025, in Nature Astronomy and the monthly notices of the Royal Astronomical Society, is a masterclass in cosmic archaeology. The team reanalyzed data from a gravitational lens first spotted decades ago in the 1990s, but they applied modern techniques and unprecedented resolution, pushing our detection threshold way, way down. Think about the sheer precision involved. A mass that is, by cosmic standards, relatively tiny, just 1 million times our Sun, nudged a beam of light as it traveled for 10 billion years. And that nudge, a flicker across an unimaginable gulf of space and time, was still distinct enough for us to notice. That's not just a discovery, it's a testament to human ingenuity. So, what's next? More rings. Many more. The James Webb Space Telescope, with its incredible infrared sensitivity, is a gravitational lens-finding machine. It's discovering them by the dozens, providing a treasure trove of new targets. With better imaging from instruments like Webb and smarter, AI-driven models to sift through the data, astronomers can now move from a single, landmark discovery to a systematic hunt. They can survey hundreds of these lenses to find more of these dark clumps. Each new detection will be another data point, allowing us to build a census of dark matter structure, to rigorously test our entire cosmological model, and to close in on the true nature of the particles that make up a quarter of our universe. This single discovery opens up a whole new way of seeing the invisible. If you want a deeper dive into the physics of gravitational lensing, the pinch trick, or the competing theories of dark matter, tell me what you're curious about in the comments, and I'll pull that thread in a future video. Because sometimes the universe's biggest secrets aren't shouted in the light of a billion stars. They're whispered in the dark, hidden in the faintest of fingerprints.